And how do interrupts work? Let me just refresh your memory. So interrupts, we have this IRQ, this interrupt request. So in fact, we might hook our little timer hardware that busily has a little counter counting down in hardware, and it counts down and it counts down long enough that, say, every 1/10 of a second, it asserts the IRQ signal. And when the IRQ is asserted, what we're going to do is basically say, okay, I'm no longer going to execute user programs. I'm going to do this forced procedure call. I'm going to save away PC+4 in this magic XP reg. That's the one that no user program gets to use. So that's how we're going to remember where the running program was in terms of where the program counter was. And then we're going to go off and simply force a new program counter, a magic program counter somewhere in the kernel code. Now you might say, well, what about saving all the other registers? I mean, you've managed to save away what the PC was, but what about R0 and R1? Well, you're right. We're going to have to take care of that, and I'm going to show you how that works now. So interrupt handling is a very, it's a small addition to the hardware. It's just it's a mechanism for doing a forced procedure call to a magic kernel procedure. We're going to actually write code that does all the rest of the work of saving a state, and then when we're executing now some code in the kernel that actually deals with interrupt. And since there's lots of different ways in which we might be interrupted, the timer goes off, the network interface has a new packet, so forth and so on. We're going to talk a little bit about how to, what the operating system looks like. And in fact, that's really the conversation for the rest of this lecture and next lecture. And when we're all done, we'll just take all this information that we've saved away in this user data structure, put it back in the hardware registers, and then return to the user program. Where do we go when we take an interrupt? Well, the beta is very simple. When you do a reset, it starts running at location 0. And if you get an illegal operation, a so-called synchronous exception, it's going to make a forced procedure call to the instruction at location 4 in main memory. And otherwise, for external interrupts, it's going to go to location 8. So you have a whole one instruction to deal with the interrupt. And of course, those instructions are branches off to now where all the rest of the code lives. Okay, so we're going to start talking. If you looked at the bottom of our little beta time train system, you'd discover that there's these 3 branches in a row that say on a reset, go here. On a synchronous exception, an illegal instruction, go to this particular location in the kernel. These are different branches to different subroutines in the kernel. Okay. Sometimes instead of having hardwired locations, there's actually what's built in hardware is the address of a table which contains where to go to. So this is the so-called interrupt table. There are a lot of different hardware schemes. It sort of doesn't matter. They all arrange very quickly to get you from starting the processing of the interrupt in the hardware to where they basically just save the program counter to setting a new program counter that's somewhere in the kernel code. Okay, and the somewhere depends on what the type of exception that we have.